Over millions of years, smaller systems collided and merged, growing larger and more complex. The Milky Way's earliest components likely formed during this period, starting as small dwarf galaxies rich in dark matter and stars. These building blocks would eventually come together, shaping the vast spiral galaxy we know today. The history of the Milky Way is marked by countless mergers and collisions with smaller galaxies. Over billions of years, these interactions added mass, introduced new stars, and shaped the structure of the Milky Way. The remnants of these ancient galaxies are still visible today, forming stellar streams and globular clusters that orbit our galaxy. One of the most significant events in the Milky Way's evolution occurred about 10 billion years ago, when it merged with a massive galaxy referred to as the Gaia Enceladus. This collision created ripples in the Milky Way's structure and enriched it with new stars and heavier elements. The Milky Way's iconic spiral arms likely formed between 6 and 9 billion years ago. As the galaxy settled into a more stable configuration, rotating gas clouds began to condense under the influence of gravity. These dense regions became star-forming nurseries, giving birth to millions of stars over millions of years. The spiral arms are dynamic, constantly reshaped by the motion of stars and interstellar matter. They are also a hub for new star formation, a process that continues to this day. At the center of the Milky Way is Sagittarius A*, a supermassive black hole with a mass equivalent to 4 million suns. This black hole likely formed in the galaxy's earliest days, growing as it consumed gas, dust, and stars from its surroundings. While it remains dormant for the most part, Sagittarius A* has played a critical role in shaping the galaxy. Its immense gravitational pull influences the orbits of stars near the galactic center and helps regulate star formation. Approximately 4.6 billion years ago, in one of the Milky Way's spiral arms, a cloud of gas and dust collapsed under gravity. This event marked the birth of our solar system. The Sun ignited at the center, while the remaining material coalesced into planets, moons, and asteroids. The Milky Way provided the raw materials for this process, enriched by generations of previous stars. Elements like carbon, oxygen, and iron, essential for life on Earth, were forged in the cores of ancient stars and spread throughout the galaxy when those stars exploded as supernovae. Today, the Milky Way spans over 100,000 light-years and contains hundreds of billions of stars, along with vast clouds of gas and dust. It is home to diverse celestial phenomena, from newborn stars to dying supernovae. The galaxy is constantly changing, with stars orbiting the center and spiral arms slowly evolving. The Milky Way also continues to grow, as it accretes material from smaller galaxies and intergalactic space. In approximately 4.5 billion years, the Milky Way will collide with its nearest large neighbor, the Andromeda Galaxy. This epic event will reshape both galaxies, forming a single, larger structure, sometimes referred to as Milkomeda. Despite the scale of the collision, individual stars are unlikely to collide due to the vast distances between them. Instead, the merger will create new regions of star formation and likely alter the central black holes of both galaxies. In the vast nothingness of pre-existence, there was only a singular point, a realm where time and space had no meaning. Then, around 13.8 billion years ago, the Big Bang erupted, an explosion of unimaginable energy that marked the birth of the universe. It was not an ordinary explosion but rather the rapid expansion of space itself, spreading matter, energy, and time across an empty void. In its infancy, the universe was a searing hot plasma, dense and chaotic. During the first fraction of a second, fundamental forces emerged: gravity, electromagnetism, and the nuclear forces, governing the interactions of particles. As the universe expanded and cooled, quarks and gluons combined to form protons and neutrons, the building blocks of atoms. Within minutes, the first elements, hydrogen and helium, were forged in a process called Big Bang nucleosynthesis. These light elements became the foundation for all future structures, including galaxies. For the next 380,000 years, the universe remained an opaque fog, where light could not travel freely. Then, the cosmos experienced a transformation as electrons and protons combined to form neutral atoms, allowing light to travel unimpeded. This event, known as recombination, marked the universe's transition to transparency. It was during this time that the first hints of structure began to emerge. Tiny fluctuations in the density of matter, amplified by gravity, created the seeds of galaxies. The stage was set for the creation of the Milky Way. Roughly 1 billion years after the Big Bang, the universe entered an era known as the Cosmic Dawn. The first stars began to shine, piercing through the darkness. These stars were unlike the ones we see today. Made almost entirely of hydrogen and helium, they burned hot and lived short, violent lives. As these early stars burned through their fuel, they created heavier elements, carbon, oxygen, and others, through nuclear fusion. When these massive stars died as supernovae, they enriched the surrounding gas clouds with these elements, enabling the formation of more complex stars and planetary systems. Around this time, gravity began pulling gas and dark matter together into larger structures. These were the first galaxies, primitive collections of stars and gas that would later merge to form larger systems. The Milky Way's earliest ancestors were among these fledgling galaxies. Small, irregular, and chaotic, they were the building blocks of what would become one of the universe's grandest structures. The Milky Way grew not through gentle accumulation but through cosmic violence. Over billions of years, smaller galaxies collided and merged, feeding the Milky Way's growth. This process, known as galactic cannibalism, shaped the galaxy's structure and composition. Evidence of these ancient collisions is still visible today. Stellar streams, made up of stars ripped from smaller galaxies, orbit the Milky Way, like celestial fossils of its turbulent past. These remnants tell the story of countless mergers, each contributing to the galaxy's mass and complexity. One of the most significant events in the Milky Way's history occurred around 10 billion years ago when it collided with a massive galaxy dubbed Gaia Enceladus. This merger added a large population of stars to the Milky Way and created ripples in its structure, shaping its evolution for billions of years. As the Milky Way grew larger, it began to take on a more organized shape. Between 6 and 9 billion years ago, it developed the iconic spiral arms we see today. These arms are not static, they are regions of higher density, created by gravitational waves that move through the galaxy like ripples in a pond. Within these spiral arms, dense clouds of gas and dust collapse to form new stars. These stellar nurseries are regions of intense activity, where the light of young stars illuminates the surrounding gas. The spiral structure is a dynamic and evolving feature, constantly reshaped by the movement of stars and interstellar matter. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius A star. With a mass equivalent to 4 million suns, this cosmic giant exerts a powerful influence over the galaxy. Sagittarius A** likely formed in the early days of the Milky Way, growing as it consumed gas, dust, and even stars. While it is relatively quiet now, it was once much more active, emitting intense radiation as it fed on surrounding material. The black hole's gravitational pull keeps the stars near the galactic center in tight orbits, creating a dense and dynamic region. Despite its destructive nature, Sagittarius A** plays a vital role in regulating the galaxy's evolution. In a quiet corner of the Milky Way, about 4.6 billion years ago, a dense cloud of gas and dust began to collapse under its own gravity. This event marked the birth of our solar system. At the center of this collapsing cloud, a young star ignited, the Sun. Around it, the remaining material formed a swirling disk, from which the planets, moons, and asteroids took shape. The Earth, our home, emerged as a rocky planet, enriched with elements like carbon and oxygen, forged in the cores of ancient stars. The Milky Way provided the raw materials for the solar system, the result of billions of years of cosmic recycling. Spanning over 100,000 light-years, the Milky Way is a vast and complex system, containing hundreds of billions of stars, along with gas, dust, and dark matter. Its spiral arms, dotted with regions of active star formation, continue to evolve. The galaxy is home to a diverse array of celestial phenomena, from massive star clusters to enigmatic black holes. It is a dynamic, living structure, shaped by gravity, star formation, and the interactions of its components. The Milky Way's story is far from over. In about 4.5 billion years, it will collide with the Andromeda Galaxy, its nearest large neighbor. This cosmic event will reshape both galaxies, creating a new, larger structure. While this collision may seem catastrophic, the vast distances between stars mean that direct collisions will be rare. Instead, the galaxies will merge gracefully, forming new regions of star formation and likely merging their central black holes. The story of the Milky Way begins in the earliest moments of the universe, nearly 13.8 billion years ago, with the Big Bang. This monumental event was not an explosion in space, but the rapid expansion of space itself. Time, space, and matter came into existence, marking the beginning of everything we know. In the first few moments after the Big Bang, the universe was a seething cauldron of energy. Elementary particles, such as quarks and electrons, formed and collided in an unimaginably hot and dense environment. Within microseconds, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. As the universe expanded, it began to cool. After about 3 minutes, protons and neutrons fused to create the first atomic nuclei, hydrogen, helium, and traces of lithium. These were the only elements present at the dawn of time, forming the foundation for all future stars and galaxies. For the next 380,000 years, the universe remained a dark, opaque fog of ionized particles. Then came a crucial transformation. Electrons combined with nuclei to form neutral atoms, allowing light to travel freely for the first time. This event, known as recombination, left behind a faint glow called the cosmic microwave background, a relic of the Big Bang still visible today. The newly transparent universe entered a phase of cooling and expansion. Tiny fluctuations in the density of matter, seeded by quantum mechanics, began to grow under the influence of gravity. These fluctuations became the scaffolding for the first cosmic structures, the ancestors of galaxies, including the Milky Way. As the universe entered its second billion years, gravity began to pull gas and dark matter into dense clumps. These regions of concentrated matter gave rise to the first stars and galaxies. These early galaxies were small and irregular, far less organized than the spiral and elliptical galaxies we see today. The first stars, known as population 3 stars, were massive and short-lived. Composed almost entirely of hydrogen and helium, they burned brightly but died quickly, often ending their lives in cataclysmic supernovae. These explosions scattered heavier elements, like carbon, oxygen, and iron, into the surrounding space, enriching the primordial gas clouds. Over time, smaller protogalaxies merged to form larger systems. The Milky Way's earliest components likely originated as small clusters of stars and gas, bound together by dark matter. These fledgling structures orbited one another in a cosmic dance, gradually coming together to form the foundation of our galaxy. The Milky Way's growth was neither peaceful nor orderly. Instead, it was a process of relentless mergers and collisions. Smaller galaxies, drawn in by the Milky Way's gravitational pull, were consumed and incorporated into its structure. This violent process, known as galactic cannibalism, is a defining characteristic of galaxy formation. One of the most significant mergers in the Milky Way's history occurred about 10 billion years ago, when it collided with a large galaxy now known as Gaia Enceladus. This event added billions of stars to the Milky Way and created a halo of stars that surrounds the galaxy today. Even now, remnants of these ancient collisions can be seen in the form of stellar streams, elongated trails of stars that were once part of smaller galaxies. These streams serve as cosmic fossils, preserving the history of the Milky Way's growth. Around 9 billion years ago, the Milky Way began to take on its iconic spiral shape. Gravity and rotational forces sculpted the galaxy's stars and gas into a flat, disk-like structure. Within this disk, density waves created regions of higher and lower density, forming the spiral arms. The spiral arms are not static structures, they are constantly reshaped by the movement of stars and gas. These regions are fertile grounds for star formation, where clouds of gas and dust collapse under gravity to create new stars. The birth of these stars illuminates the arms, making them some of the brightest and most dynamic features of the Milky Way. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A star. This mysterious object, with a mass equivalent to 4 million suns, plays a crucial role in the galaxy's evolution. While Sagittarius A** is relatively inactive now, it was likely much more energetic in the past. In its youth, it fed on surrounding gas and stars, emitting powerful jets of energy that influenced the galaxy's growth. Today, its immense gravitational pull anchors the stars near the galactic center, maintaining the structure of the Milky Way. About 4.6 billion years ago, in a quiet region of the Milky Way, a cloud of gas and dust began to collapse under gravity. This marked the beginning of our solar system. At the center of the collapsing cloud, a young star ignited, the Sun. Around it, the remaining material formed a protoplanetary disk, from which the planets, moons, and asteroids were born. The Earth formed as a rocky planet, enriched with elements forged in the hearts of ancient stars. The Sun and its planets are part of the Milky Way's Orion arm, one of its smaller spiral arms. Here, far from the chaotic center, conditions were calm enough to allow life to emerge and thrive. The Milky Way is a vast, dynamic system, spanning over 100,000 light-years and containing hundreds of billions of stars. Its spiral arms are sites of active star formation, while its central bulge is a dense region filled with older stars. The galaxy also contains vast quantities of dark matter, an invisible substance that provides the gravitational glue holding it together. Surrounding the galaxy is a halo of stars and globular clusters, remnants of the Milky Way's tumultuous past. The Milky Way's story is far from over. In about 4.5 billion years, it will collide with the Andromeda Galaxy, its nearest large neighbor. This cosmic event will reshape both galaxies, creating a new structure often referred to as Milkometa. The collision will not result in catastrophic destruction. Instead, it will trigger waves of star formation and lead to the merging of the central black holes of both galaxies. The new galaxy will be a testament to the Milky Way's enduring legacy. The universe was born in an instant of incomprehensible density and temperature. Imagine a space smaller than an atom, containing all the energy that would ever exist. In a flash, this energy expanded, creating the fabric of space and time. The Big Bang wasn't a typical explosion, it was the rapid unfolding of space itself, stretching everything outward like the surface of a balloon. In the first fractions of a second, the universe was governed by a force we can hardly comprehend, a unified field that quickly split into the forces of nature we know today. Gravity, the weakest but most far-reaching force, began to pull matter together. Electromagnetism governed light and atoms, while strong and weak nuclear forces shaped the particles within atomic nuclei. As the universe cooled to a few trillion degrees, quarks and gluons condensed into protons and neutrons. These particles danced in a dense sea of photons, colliding and interacting in chaotic harmony. Over the next 3 minutes, the temperature dropped enough for these protons and neutrons to fuse into the first atomic nuclei. This was the beginning of the cosmic alchemy that would eventually lead to stars, planets, and life. For the next 380,000 years, the universe was a hot plasma of charged particles. Light was trapped, endlessly scattering in the opaque fog. But as temperatures cooled further, electrons paired with nuclei to form neutral atoms. Suddenly, the universe became transparent, and light from this epoch began its long journey across space. This light, stretched by billions of years of expansion, became the cosmic microwave background, a faint afterglow of the Big Bang still visible today. This era marked the end of chaos and the beginning of structure. Tiny irregularities in the density of matter, amplified by gravity, created regions where galaxies would eventually form. The universe was now ready for its next chapter. As the universe expanded, the vast, empty void was not entirely uniform. Small regions of higher density attracted more matter through gravity, forming clumps that would grow into the first galaxies. These clumps consisted primarily of dark matter, an invisible substance that outweighs ordinary matter and acts as the scaffolding for cosmic structures. The first stars ignited in these regions, marking the dawn of starlight. These population 3 stars were colossal, hundreds of times the mass of the Sun. Their lifespans were brief, mere millions of years, but their influence was profound. When these stars exploded as supernovae, they enriched the surrounding gas with heavier elements, paving the way for more complex stars and planets. Over millions of years, these primitive galaxies merged to form larger ones. Each collision was a dramatic event, releasing massive amounts of energy and triggering waves of star formation. The Milky Way's ancestors were among these early galaxies, growing through mergers and accreting gas from the intergalactic medium. The history of the Milky Way is a tale of survival and growth. Gravity pulled smaller galaxies into its orbit, tearing them apart and absorbing their stars, gas, and dark matter. Each merger added to the galaxy's mass, reshaping its structure and introducing new populations of stars. These interactions were not gentle. As smaller galaxies approached, tidal forces stretched and distorted them, creating long streams of stars. These stellar streams, still visible today, are evidence of the Milky Way's violent past. Over billions of years, these remnants were assimilated, becoming part of the galaxy's halo and disk. One of the most significant events in the Milky Way's history was its collision with Gaia Enceladus, a massive galaxy that merged with ours about 10 billion years ago. This collision reshaped the Milky Way, creating a thicker disk of stars and enriching it with heavier elements. It was a transformative period, marking the transition from a chaotic, irregular structure to the more organized galaxy we see today. The formation of the Milky Way's spiral arms was a gradual process, influenced by the galaxy's rotation and internal dynamics. As the galaxy spun, gravitational forces created density waves, regions where stars and gas were more concentrated. These waves acted like traffic jams in space, slowing down stars and compressing gas clouds. In these compressed regions, new stars were born, illuminating the spiral arms and giving them their iconic appearance. The process is ongoing. The spiral arms are not fixed structures but constantly changing as stars and gas move through them. The Milky Way's spiral arms are also rich in molecular clouds, vast reservoirs of gas and dust that serve as the raw material for star formation. These clouds are shaped by the interplay of gravity, turbulence, and magnetic fields, creating a complex environment where stars are born in clusters. The Milky Way's center is a region of extremes. At its heart lies Sagittarius A*, a supermassive black hole surrounded by a dense cluster of stars. Sagittarius A* has a mass equivalent to 4 million suns, yet it occupies a region no larger than our solar system. This black hole exerts a powerful gravitational pull, influencing the orbits of nearby stars and shaping the dynamics of the galactic center. While Sagittarius A* is relatively quiet now, it was likely much more active in the past, emitting intense radiation as it consumed gas and stars. These periods of activity may have shaped the distribution of stars and gas in the inner galaxy. The discovery of Sagittarius A* is one of astronomy's great achievements. Observations of stars orbiting the black hole provided direct evidence of its existence, offering a glimpse into the mysterious nature of these cosmic giants. In one of the Milky Way's spiral arms, about 4.6 billion years ago, a cloud of gas and dust began to collapse. This region, enriched with elements from previous generations of stars, was the birthplace of the solar system. At the center of the collapsing cloud, a protostar formed, the Sun. Around it, a rotating disk of gas and dust took shape, giving rise to planets, moons, and asteroids. The Earth, forming in the habitable zone, became a rocky planet with the potential for life. The Milky Way provided the ingredients for this process. Elements like carbon, oxygen, and iron, essential for life on Earth, were forged in the cores of massive stars and spread across the galaxy through supernovae. The solar system is a testament to the galaxy's ability to recycle its materials, creating new stars and planets from the remnants of the old. The Big Bang set the stage for the cosmos, but in its immediate aftermath, there was no Milky Way, no stars, and certainly no planets. Instead, the universe was a hot, dense sea of particles, existing in a state of pure chaos. As it expanded, it began to cool. Quarks combined to form protons and neutrons, and within minutes, the first atomic nuclei emerged. Hydrogen dominated this early era, with helium and trace amounts of lithium rounding out the elemental composition. This primordial mix was the starting point for everything that would follow. The process of cooling and expansion was not uniform. Tiny variations in density, caused by quantum fluctuations during inflation, created a cosmic tapestry. These denser regions became gravitational wells, pulling in more matter over time. These seeds would grow into the first galaxies, but that stage was still hundreds of millions of years away. For nearly 400,000 years, the universe remained dark, filled with a plasma of charged particles that trapped light. This period, known as the Dark Ages, ended when atoms formed, and light finally broke free. This light, the cosmic microwave background, carries the fingerprint of the universe's birth. As the universe entered its second billion years, gravity began its relentless work. Regions of higher density grew denser, attracting gas and dark matter to form the first halos. These halos were the cradles of the first stars. The first stars were Titans, population 3 stars that burned through their fuel at an extraordinary rate. Their cores acted as cosmic forges, creating heavier elements through nuclear fusion. When they died as supernovae, they seeded the surrounding gas with these elements, enriching the material that would form the next generation of stars. Over time, these stars grouped into the first galaxies. Unlike the majestic spirals and ellipticals we see today, these early galaxies were small and irregular, shaped by the chaotic interplay of gravity and gas. The Milky Way began as one of these small proto-galaxies, a mere fragment in the vast expanse of space. The young Milky Way was not a single, coherent structure but a collection of smaller galaxies orbiting a common center. Over billions of years, these galaxies merged through the force of gravity. The process was anything but gentle. As smaller galaxies approached, tidal forces ripped them apart, creating long streams of stars and gas. These remnants became part of the growing Milky Way, their stars dispersed into the galaxy's halo and disk. Gaia Enceladus was one such galaxy. Its merger with the Milky Way, around 10 billion years ago, was a defining moment in our galaxy's history. It brought a vast number of stars, enriched the galaxy with heavier elements, and created ripples in its structure. Today, we can still see the evidence of this event in the stars that form the thick disk of the Milky Way. Even now, the Milky Way continues to grow through mergers. The Sagittarius dwarf galaxy, for instance, is currently being consumed, adding its stars and gas to the galactic disk. As the Milky Way grew larger, its shape began to evolve. Initially, it was a chaotic, irregular collection of stars and gas. Over time, as it rotated and settled, it developed a more organized structure. The spiral arms are one of the Milky Way's most striking features. These arms are not fixed, they are density waves that move through the galaxy, compressing gas and triggering star formation as they go. The stars themselves move in and out of these arms, like cars on a highway passing through areas of congestion. The spiral structure is also influenced by the galaxy's rotation. As the Milky Way spins, gravity and angular momentum work together to maintain the disk's flat shape. This rotation also helps to distribute stars and gas, creating the intricate patterns we see today. At the heart of the Milky Way lies a region of incredible extremes. Sagittarius A*, the supermassive black hole at the center, is a point of immense gravitational pull. Surrounding it is a dense cluster of stars, orbiting at incredible speeds. Sagittarius A** likely formed in the early days of the galaxy, growing as it consumed gas, stars, and other material. While it is relatively dormant now, its past activity shaped the central region of the galaxy. Powerful winds and radiation from the black hole influenced the distribution of gas, limiting star formation in its immediate vicinity. Studying Sagittarius A** has been a monumental achievement in modern astronomy. Observations of stars orbiting the black hole provided direct evidence of its existence and offered insights into the nature of these enigmatic objects. Around 4.6 billion years ago, in a quiet arm of the Milky Way, a cloud of gas and dust began to collapse under gravity. This event marked the birth of the solar system. The collapse formed a protostar at the center, the Sun. Around it, the remaining material flattened into a disk, where particles collided and stuck together, eventually forming planets. The inner planets, like Earth, formed from heavier elements, while the outer planets, composed largely of gas, took shape farther from the Sun. The elements that made this possible, carbon, oxygen, silicon, and others, were forged in the cores of stars and spread across the galaxy by supernovae. The solar system is a product of billions of years of cosmic recycling, a testament to the Milky Way's ability to create new worlds from the remnants of old ones. The Milky Way is a vast, complex structure. Its disk spans over 100,000 light-years and contains hundreds of billions of stars, along with vast quantities of gas and dust. Surrounding the disk is the halo, a spherical region populated by old stars and globular clusters. At the center lies the galactic bulge, a dense region filled with older stars. This area is the Milky Way's ancient heart, home to some of the galaxy's oldest stars and its supermassive black hole. The Milky Way is constantly changing. Stars are born in the spiral arms, live for millions or billions of years, and die, enriching the galaxy with the elements needed for the next generation. It is a dynamic, living system, shaped by gravity, star formation, and cosmic interactions. The Milky Way's story is far from over. In about 4.5 billion years, it will collide with the Andromeda Galaxy, its nearest large neighbor. This collision will not destroy either galaxy but will reshape them both, creating a new, larger structure. During the collision, gas clouds will compress, triggering waves of star formation. The central black holes of the two galaxies will likely merge, creating an even larger supermassive black hole. The resulting galaxy, often referred to as Milky, will be a testament to the ongoing evolution of the cosmos. Even after this event, the remnants of the Milky Way will continue to drift through the universe, part of the never-ending cycle of cosmic creation and destruction. In the beginning, time and space were one, confined to an infinitesimal point of infinite density and temperature. Then, in a fraction of a second, the Big Bang unraveled this singularity, setting the cosmos in motion. Space itself expanded faster than the speed of light, carrying with it the fundamental ingredients of existence. The early universe was a roiling plasma of quarks and gluons. Protons and neutrons formed mere seconds after the Big Bang, colliding to create the first atomic nuclei. However, these nuclei could not yet form atoms. The intense heat kept electrons and nuclei from binding, leaving the universe as a charged, opaque fog. For the next few 100,000 years, gravity worked silently. Regions with slightly higher densities began to grow, pulling in more matter. This epoch saw the formation of vast cosmic structures invisible to the eye, dark matter halos. These halos would eventually become the gravitational anchors for galaxies. When the universe cooled enough for electrons to combine with nuclei, light could finally escape the plasma. This light became the cosmic microwave background, a faint glow still visible today in a crucial map of the universe's infancy. It reveals the tiny density fluctuations that would become the seeds of all cosmic structures, including the Milky Way. Gravity does not rest. Over the next few 100 million years, it continued to pull gas and dark matter into clumps. In these dense regions, the first stars ignited, marking the end of the Dark Ages and the dawn of the first galaxies. These galaxies were not the ordered spirals or majestic ellipticals of today. They were chaotic assemblies of stars, gas, and dark matter, shaped by their environment and the violent interactions between their components. The first stars, population 3 stars, were unlike anything that exists today. They were massive, hundreds of times the mass of our Sun, and composed almost entirely of hydrogen and helium. Their lifespans were short, ending in supernovae that enriched the surrounding gas with heavier elements. This enrichment laid the groundwork for the next generation of stars, capable of forming planets and complex systems. Over time, these small galaxies began to merge, forming larger systems. The Milky Way was born from these mergers, a patchwork of ancient stars and new formations, constantly evolving under the influence of gravity. The Milky Way's growth was marked by violence and destruction. Smaller galaxies were drawn into its gravitational well, stripped of their stars and gas, and consumed. This process, known as galactic cannibalism, is a common mechanism of galaxy growth. The mergers weren't random. They followed the contours of dark matter filaments, the invisible framework of the cosmos. As galaxies moved along these filaments, they collided and merged, transferring their mass to larger systems like the Milky Way. Gaia Enceladus was one such galaxy. When it collided with the Milky Way around 10 billion years ago, it left a lasting imprint. Its stars were distributed throughout the thick disk and halo, and its gas fueled a burst of star formation that reshaped the galaxy. The evidence of these mergers is written in the stars. Stellar streams, long ribbons of stars that arc across the sky, are the remnants of galaxies torn apart by the Milky Way's gravity. These streams provide a window into the galaxy's tumultuous past, revealing the traces of ancient collisions that shaped its present form. As the Milky Way evolved, it began to settle into a more stable configuration. Its stars, gas, and dust formed a flat, rotating disk, influenced by angular momentum and gravitational interactions. The spiral arms are one of the galaxy's most distinctive features, but they are not solid structures. Instead, they are density waves, areas where gas and stars are temporarily compressed. These waves move through the disk, triggering star formation as they go. This process is ongoing. As stars form in the spiral arms, they illuminate the surrounding gas, creating bright regions that highlight the arm's structure. Meanwhile, older stars drift out of the arms, spreading across the disk. The Milky Way's spiral structure is a dynamic and ever-changing feature. It is shaped by interactions with satellite galaxies, gravitational forces within the disk, and the continuous motion of its stars and gas. At the center of the Milky Way lies a region of mystery and extremes, Sagittarius A*, a supermassive black hole that exerts a profound influence on the galaxy. Sagittarius A** is surrounded by a dense cluster of stars, many of which orbit at incredible speeds. These orbits provided the first direct evidence of the black hole's existence, allowing astronomers to calculate its mass, 4 million times that of the Sun. While it is relatively quiet today, Sagittarius A** likely played a more active role in the past. During its active phase, it would have consumed vast amounts of gas and dust, emitting powerful jets of radiation and shaping the central region of the galaxy. The presence of a supermassive black hole is not unique to the Milky Way. Most large galaxies harbor one at their center, suggesting that these objects are a natural outcome of galaxy formation. However, their origins and evolution remain one of astronomy's greatest mysteries. In the Orion arm of the Milky Way, about 4.6 billion years ago, a quiet region of gas and dust began to collapse. This marked the birth of our solar system. The collapse formed a protostar, the Sun, at the center, surrounded by a rotating disk of gas and dust. Over time, particles in the disk collided and stuck together, forming planetesimals, the building blocks of planets. The Earth formed in the inner region of the disk, where temperatures were high enough to vaporize ice. This region produced rocky planets, while the outer disk, colder and richer in ices, gave rise to gas giants like Jupiter and Saturn. The solar system is a microcosm of the Milky Way's history. Its composition reflects billions of years of cosmic recycling, from the formation of the first stars to the enrichment of the galaxy with heavy elements. The Milky Way is not static. Its disk rotates, its stars orbit the galactic center, and new stars are born while old ones die. Its spiral arms are regions of intense activity, where gravity compresses gas into star-forming clouds. The galaxy's halo is home to some of its oldest stars, remnants of the first galaxies that merged to form the Milky Way. These stars provide a glimpse into the galaxy's distant past, preserving the chemical signatures of an earlier universe. Meanwhile, the central bulge is a dense region of old stars, a relic of the galaxy's early years. It surrounds Sagittarius A**, which continues to influence the orbits of nearby stars. The Milky Way's story will culminate in an epic collision with the Andromeda Galaxy. This event, set to occur in about 4.5 billion years, will reshape both galaxies. As the galaxies merge, their stars will be flung into new orbits, creating a massive elliptical galaxy. Gas clouds will collide, triggering bursts of star formation. The central black holes of both galaxies will merge, forming an even larger supermassive black hole. Even after this dramatic event, the Milky Way's legacy will endure. Its stars, planets, and remnants will continue to drift through space, part of the endless cycle of cosmic evolution. The origin of the Milky Way begins not with itself but with the universe. Imagine a time before time, a singularity, infinitely small, infinitely dense, holding within it the potential for everything. This singularity erupted in what we call the Big Bang, approximately 13.8 billion years ago. In its initial moments, the universe was an expanding plasma of energy, where particles like quarks and gluons formed. The conditions were so extreme that these particles could not combine into anything stable. Within milliseconds, however, the temperature dropped, and quarks combined to form protons and neutrons, the building blocks of atomic nuclei. As the universe continued to cool, nuclei formed in a process called nucleosynthesis, producing hydrogen, helium, and a trace of lithium. This primordial mix accounted for nearly all the ordinary matter in the cosmos. For hundreds of thousands of years, the universe was a dark, hot fog, where photons, light particles, bounced endlessly off charged particles, unable to escape. This period, known as the Dark Ages, ended when the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This event released photons, creating the cosmic microwave background, a faint glow of radiation that scientists can still detect today. Gravity began to work on the slight density variations present in the universe, amplifying them. Over millions of years, these small differences grew into dense regions that became the cradles of galaxies. The first stars ignited roughly 200 million years after the Big Bang, marking the end of the Dark Ages. These massive population III stars burned hot and bright, their light carving through the surrounding darkness. But they lived short lives, exploding as supernovae and dispersing heavier elements like carbon and oxygen into space. The first galaxies formed as clusters of these stars, surrounded by halos of dark matter. These primitive galaxies were small and irregular, growing larger through collisions and mergers. They lacked the defined shapes of spirals and ellipticals, appearing chaotic and turbulent. As gravity drew in more material, these galaxies began to organize themselves. The Milky Way's ancestors emerged during this time, small and fragmented. They were among the countless young galaxies scattered across the early universe, each vying for growth in a chaotic cosmic arena. Galaxies grow by consuming smaller galaxies, and the Milky Way was no exception. Over billions of years, it absorbed countless dwarf galaxies, adding their stars, gas, and dark matter to its own. This process of galactic cannibalism is a violent yet essential aspect of galaxy evolution. Evidence of these mergers is preserved in the form of stellar streams, elongated arcs of stars that were once part of smaller galaxies. These streams orbit the Milky Way, remnants of its turbulent past. One of the most significant mergers occurred about 10 billion years ago, when the Milky Way collided with the Gaia-Enceladus galaxy. This event added billions of stars to the Milky Way, forming its thick disk and enriching it with heavier elements. It also triggered a burst of star formation, illuminating the galaxy in brilliant light. The process of galactic cannibalism continues today. The Sagittarius dwarf galaxy, for example, is being torn apart by the Milky Way's gravity, contributing new stars and gas to its growing structure. About 9 billion years ago, the Milky Way began to settle into its familiar shape. Its disk formed as gas and stars flattened into a rotating plane under the influence of angular momentum. Over time, the galaxy developed its iconic spiral arms. These arms are not fixed structures but density waves, regions where gas and stars are more concentrated. As material moves through these waves, it slows down and compresses, triggering the formation of new stars. The result is a dynamic, self-sustaining cycle of star formation. The spiral arms are also rich in molecular clouds, vast reservoirs of gas and dust. These clouds are the birthplace of stars, where gravity overcomes internal pressure to create dense, luminous clusters. Today, the Milky Way's spiral arms remain active regions of star formation, illuminated by the light of young, massive stars. At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole with a mass equivalent to 4 million suns. Despite its immense gravity, Sagittarius A* is relatively quiet, consuming very little material compared to more active black holes in other galaxies. The discovery of Sagittarius A* was a milestone in modern astronomy. By observing the orbits of stars near the galactic center, scientists calculated the mass and size of this invisible giant, confirming its existence. While it may seem dormant now, Sagittarius A* likely played a more active role in the galaxy's past. During its active phases, it emitted powerful jets of energy, shaping the surrounding environment and influencing the distribution of gas and stars. About 4.6 billion years ago, a quiet region within one of the Milky Way's spiral arms gave rise to our solar system. A cloud of gas and dust began to collapse under its own gravity, forming a protostar at its center. This protostar became the Sun. Around the Sun, the remaining material flattened into a disk. Over time, particles in this disk collided and stuck together, forming planetesimals, the building blocks of planets. These planetesimals grew larger, eventually forming the planets, moons, and other bodies that make up our solar system. The Earth, located in the Sun's habitable zone, became a rocky planet with the potential for life. Its composition reflects the enrichment of the Milky Way over billions of years, containing elements forged in the cores of ancient stars. Today, the Milky Way is a vast, dynamic system. Its disk spans over 100,000 light-years, containing hundreds of billions of stars, along with gas, dust, and dark matter. Surrounding the disk is a halo populated by ancient stars and globular clusters, remnants of the galaxy's formation. The Milky Way's central bulge is a dense region filled with older stars, while its spiral arms are vibrant sites of star formation. The galaxy is also home to numerous satellite galaxies, including the Large and Small Magellanic Clouds, which orbit the Milky Way like cosmic companions. The Milky Way's story is far from over. In about 4.5 billion years, it will collide with the Andromeda Galaxy, its nearest large neighbor. This event will reshape both galaxies, merging them into a new, larger structure. During the collision, gas clouds will compress, triggering waves of star formation. The central black holes of the Milky Way and Andromeda will merge, creating an even larger supermassive black hole. The resulting galaxy, often called Milkomeda, will be an elliptical system, marking the next chapter in the Milky Way's evolution. Even in its new form, the legacy of the Milky Way will endure, carried by its stars and the elements that make up planets like Earth. The story of the Milky Way begins with the very fabric of the cosmos itself. In the seconds after the Big Bang, the universe was a seething ocean of energy, where matter and antimatter annihilated each other in a cosmic battle. Yet, matter slightly outweighed antimatter, leaving a small but crucial amount to form the stars and galaxies we know today. Within minutes of the Big Bang, the temperature of the universe dropped below 1 billion degrees Celsius, enabling the formation of atomic nuclei. Hydrogen and helium emerged as the dominant elements, their simple structures resilient in the face of the universe's harsh conditions. But these basic atoms were only the first chapter in a long journey toward complexity. As the universe expanded, it cooled further. Roughly 380,000 years later, electrons combined with nuclei to form neutral atoms, releasing light for the first time. This light, now stretched into microwaves, provides a snapshot of the infant universe. Known as the cosmic microwave background, it reveals the tiny ripples in density that would eventually grow into galaxies. In this vast and nearly empty universe, dark matter played a vital role. Though invisible and undetectable through conventional means, dark matter's gravitational pull began gathering hydrogen and helium into vast clouds. These clouds became the cradles of the first galaxies. The transition from chaos to order began slowly. Gravity acted as the sculptor, pulling matter into dense regions. Over hundreds of millions of years, these dense areas grew hotter and more compressed until the first stars ignited. These stars illuminated the universe, marking the end of the Dark Ages. These early galaxies were small and irregular, composed of clusters of stars surrounded by halos of dark matter. They lacked the intricate structures of later galaxies, instead appearing as chaotic collections of light and matter. The Milky Way's ancestors emerged during this epoch. They were tiny compared to the modern galaxy, but they carried the seeds of its future greatness. As these proto-galaxies merged, they began to take on more defined shapes, laying the foundation for the Milky Way. The first stars, known as Population 3 stars, played a critical role in this era. Their immense size and heat allowed them to forge heavier elements in their cores, but their lives were fleeting. When they exploded as supernovae, they scattered these elements into the surrounding gas, enriching the cosmos and setting the stage for the next generation of stars. The growth of the Milky Way was a process of destruction and creation. Over billions of years, smaller galaxies were drawn into its gravitational pull. These galaxies were torn apart, their stars and gas absorbed into the larger system. The remnants of these mergers are still visible today. Stellar streams, long ribbons of stars stretched across the sky, trace the paths of smaller galaxies consumed by the Milky Way. Each of these streams tells a story, a record of the galaxy's tumultuous history. One of the most dramatic collisions occurred around 10 billion years ago, when the Milky Way encountered the Gaia Enceladus galaxy. This merger added significant mass to the galaxy and triggered a burst of star formation. The thick disk of the Milky Way, a component distinct from its thinner, more organized disk, is a legacy of this event. The Milky Way continues to grow in this way. Satellite galaxies like the Sagittarius dwarf galaxy are currently being disrupted by tidal forces, their stars gradually joining the Milky Way's halo. About 9 billion years ago, the Milky Way began to take on its iconic spiral shape. This transformation was driven by the rotation of its disk, which organized its stars and gas into a flat plane. The spiral arms are regions of higher density within this plane. These density waves move through the galaxy, compressing gas clouds and triggering star formation. The arms are not static structures but dynamic patterns that shift over time, shaped by gravitational forces and the motion of stars. Star formation within the spiral arms creates a cycle of renewal. Massive stars form quickly, live brief but brilliant lives, and die in supernovae, scattering their enriched material into the surrounding space. This material becomes the building blocks for new stars, continuing the cycle. At the center of the Milky Way lies Sagittarius A*, a supermassive black hole whose gravity dominates the inner regions of the galaxy. With a mass equivalent to 4 million suns, this object is a gravitational anchor for the stars and gas near the galactic center. The discovery of Sagittarius A* was a turning point in astrophysics. By observing the orbits of stars near the center, astronomers calculated its mass and confirmed that it must be a black hole. While it is relatively inactive now, Sagittarius A* has likely influenced the Milky Way's evolution in profound ways. During periods of activity, it would have emitted powerful jets of energy, affecting the distribution of gas and potentially suppressing star formation in its vicinity. Approximately 4.6 billion years ago, within one of the Milky Way's spiral arms, a cloud of gas and dust began to collapse under gravity. This event marked the birth of our solar system. The Sun formed at the center of this collapsing cloud, surrounded by a rotating disk of material. Over time, particles in this disk collided and stuck together, forming the planets, moons, and other bodies that orbit the Sun today. The Earth, uniquely positioned in the Sun's habitable zone, became a rocky planet capable of supporting life. Its composition reflects the long history of the Milky Way, enriched by billions of years of stellar evolution and supernovae. The Milky Way is a massive, complex structure, spanning over 100,000 light-years and containing hundreds of billions of stars. Its disk rotates at speeds exceeding 200 kilometers per second, while its central bulge houses some of the galaxy's oldest stars. The galaxy is also surrounded by a halo of dark matter, which provides the gravitational framework that holds it together. This halo contains ancient globular clusters, remnants of the Milky Way's earliest days. The Milky Way's spiral arms are active sites of star formation, while its central regions are dominated by older, more evolved stars. Together, these components create a dynamic system that continues to evolve. The Milky Way's journey is far from over. In about 4.5 billion years, it will collide with the Andromeda Galaxy, initiating a cosmic dance that will reshape both galaxies. The collision will not destroy stars or planets, as the distances between them are vast. Instead, the galaxies will merge into a single, larger structure. During this process, gas clouds will compress, triggering intense star formation. The central black holes of the Milky Way and Andromeda will eventually merge, forming an even larger supermassive black hole. The resulting galaxy, often referred to as Milkomeda, will be an elliptical system, marking the next chapter in the Milky Way's story. The Big Bang was not just an explosion, it was the birth of the fabric of reality. The sudden expansion of space-time created the universe as we know it, filled with boundless energy. Within a billionth of a second, the cosmos expanded exponentially, a process known as inflation. During inflation, quantum fluctuations, the tiniest variations in density, were stretched to cosmic scales. These fluctuations would become the seeds for galaxies, forming the cosmic web of matter that structures the universe today. The universe at this time was unrecognizable. Temperatures were trillions of degrees, and particles like quarks, leptons, and gluons zipped around at near-light speeds. The laws of physics were just beginning to settle into their current form. 3 minutes after the Big Bang, the universe cooled enough for nuclear reactions to occur, forming the first atomic nuclei, mostly hydrogen and helium. These elements filled the cosmos, but the next stage of evolution would take much longer. The universe spent hundreds of thousands of years cooling and expanding. During this time, it remained a dark fog, with light unable to travel freely. But gravity was at work, slowly pulling matter into denser regions. At around 380,000 years after the Big Bang, the universe transitioned into transparency. Electrons combined with nuclei to form neutral atoms, allowing photons to stream across space. This event, known as recombination, gave birth to the cosmic microwave background, a snapshot of the early universe that we still observe today. This was the foundation on which the Milky Way and every other galaxy would eventually be built. Gravity, the universe's great architect, continued to work on the primordial gas of hydrogen and helium. In the densest regions, dark matter, an invisible yet massive substance, acted as a scaffolding, pulling ordinary matter into vast structures. In these pockets of gas, the first stars were born. They were immense, short-lived, and entirely different from the stars we see today. Composed only of hydrogen and helium, they burned at astonishing temperatures, fusing light elements into heavier ones like carbon, oxygen, and iron. When these first stars exploded as supernovae, they scattered these elements into the surrounding gas, enriching it. This material would eventually form the next generation of stars and planets. Small galaxies, irregular in shape and chaotic in composition, began to form. These proto-galaxies collided and merged, growing larger and more organized over time. The Milky Way's ancestors were among them, small and fragmented, yet filled with the potential to become something extraordinary. The Milky Way's growth was not a gentle process. Over billions of years, it grew by consuming smaller galaxies, tearing them apart with tidal forces and absorbing their stars and gas. These mergers were transformative events. They not only added mass to the Milky Way but also triggered waves of star formation, lighting up the galaxy with newly born stars. One of the most significant mergers was with the Gaia-Enceladus galaxy around 10 billion years ago. This event fundamentally reshaped the Milky Way, forming its thick disk and enriching it with new stars and heavier elements. Even today, the Milky Way continues to consume smaller galaxies. The Sagittarius dwarf galaxy, for example, is currently being pulled apart, its stars stretched into long streams that orbit the Milky Way. These stellar streams, visible to astronomers, act as cosmic fossils, preserving the history of the galaxy's growth. They reveal a story of relentless accumulation, where destruction and creation go hand in hand. The Milky Way's iconic spiral structure began to take shape around 9 billion years ago. As the galaxy rotated, the combined effects of gravity and angular momentum organized its stars and gas into a flat, rotating disk. The spiral arms are a result of density waves, regions where stars and gas are temporarily compressed. These waves move through the disk like ripples on a pond, triggering star formation as they pass. Within these arms, dense clouds of gas collapse to form new stars. The most massive of these stars live short lives, illuminating the arms and creating brilliant regions of light and color. Over billions of years, the spiral arms have continually evolved, shaped by the movement of stars, the influence of gravity, and the interactions with smaller galaxies. Today, the Milky Way's spiral arms remain some of the most active and vibrant regions of the galaxy. The Milky Way's central region, known as the galactic bulge, is home to Sagittarius A*, a supermassive black hole. With a mass of 4 million suns, it is a gravitational powerhouse that anchors the galaxy's core. Sagittarius A* is surrounded by a dense cluster of stars, many of which orbit at extraordinary speeds. These orbits provided the first direct evidence of the black hole's existence, as astronomers could calculate its mass based on the movement of nearby stars. While Sagittarius A* is relatively quiet today, it was likely much more active in the past. During these active phases, it would have emitted powerful jets of radiation, shaping the distribution of gas in the central regions of the galaxy. The presence of a supermassive black hole is a common feature of large galaxies. It suggests that the formation of such objects is closely tied to the process of galaxy evolution. Yet many questions remain about their origins and influence over cosmic time. In a quiet region of the Milky Way's Orion arm, around 4.6 billion years ago, a cloud of gas and dust began to collapse under gravity. This marked the birth of our solar system. At the center of this collapsing cloud, a protostar ignited, the Sun. Around it, the remaining material formed a rotating disk, from which the planets, moons, and asteroids emerged. The Earth formed as a rocky planet, enriched with elements like carbon, oxygen, and silicon, all forged in the cores of previous generations of stars. Its position in the Sun's habitable zone allowed it to retain liquid water, creating the conditions for life to emerge. The Solar System is a microcosm of the Milky Way's history, shaped by billions of years of cosmic evolution. Its formation reflects the galaxy's ability to recycle material, creating new worlds from the remnants of old ones. The Milky Way is a vast and dynamic system, stretching over 100,000 light-years and containing hundreds of billions of stars. Its spiral arms are regions of intense activity, where new stars are born from clouds of gas and dust. The central bulge is a dense region filled with older stars, while the surrounding halo contains ancient globular clusters and streams of stars from past mergers. The galaxy is also surrounded by an invisible halo of dark matter, which provides the gravitational framework that holds it together. Without dark matter, the Milky Way's stars would not orbit fast enough to stay bound to the galaxy. The Milky Way's journey is far from over. In about 4.5 billion years, it will collide with the Andromeda Galaxy, its nearest large neighbor. This collision will create a spectacular cosmic event, reshaping both galaxies. During the merger, gas clouds will compress, igniting waves of star formation. The central black holes of the Milky Way and Andromeda will merge, forming an even larger supermassive black hole. The resulting galaxy, often called Milkomeda, will be an elliptical system. Though it will look very different, the legacy of the Milky Way will endure, carried by its stars and the elements that once formed planets like Earth. The Big Bang was the ultimate act of creation, a moment that set time, space, and matter into motion. Yet, in its aftermath, the universe was a hostile and unrecognizable place. Temperatures soared into trillions of degrees, and particles like quarks and gluons collided violently in a primordial soup. As the universe expanded, it cooled. Within microseconds, quarks grouped into protons and neutrons. By the time the universe was 3 minutes old, these particles had begun fusing into the first atomic nuclei. Hydrogen and helium emerged as the dominant elements, making up nearly all the matter in the cosmos. For hundreds of thousands of years, light remained trapped, bouncing endlessly through the hot plasma of charged particles. The cosmos was dark and chaotic, with no stars, planets, or galaxies, only a fog of hydrogen and helium. This era, known as the Dark Ages, persisted until the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. At this moment of recombination, the universe became transparent, allowing light to travel freely for the first time. This ancient light, now stretched into microwaves by billions of years of cosmic expansion, is the cosmic microwave background. It provides us with a detailed image of the infant universe, revealing the seeds of what would grow into galaxies, including the Milky Way. The Dark Ages ended with the birth of the first stars, approximately 200 million years after the Big Bang. These population 3 stars, composed entirely of hydrogen and helium, were colossal, burning brightly and dying young. They seeded the universe with heavier elements, paving the way for future generations of stars and planets. As more stars ignited, gravity pulled them into clusters, forming the first galaxies. These galaxies were small, irregular, and chaotic, far removed from the grand spirals and ellipticals we see today. They collided frequently, merging into larger systems in a violent but creative process. The Milky Way began as one of these proto-galaxies, a small and unassuming structure among countless others. Over time, it grew, absorbing smaller galaxies and accumulating gas and dark matter. This was the beginning of its transformation into the sprawling spiral galaxy we know today. The growth of the Milky Way is a story of survival and dominance. Over billions of years, it expanded by consuming smaller galaxies. These collisions were not gentle, they tore apart the smaller systems, scattering their stars and gas into the Milky Way's halo and disk. The evidence of these ancient mergers is preserved in the form of stellar streams, long trails of stars that trace the paths of disrupted galaxies. These streams are relics of a violent past, offering astronomers a window into the Milky Way's evolution. One of the most transformative events in the Milky Way's history occurred around 10 billion years ago. A massive galaxy, Gaia Enceladus, collided with the Milky Way, merging its stars and gas into the growing system. This event created the thick disk of the galaxy and enriched it with elements forged in Gaia Enceladus's stars. Even now, the process of galactic cannibalism continues. The Sagittarius dwarf galaxy, for instance, is being pulled apart by the Milky Way's gravity, its stars gradually joining the larger galaxy. The Milky Way's iconic spiral arms began to form about 9 billion years ago, as the galaxy settled into a rotating disk. These arms are not fixed structures but patterns created by density waves, regions of higher gravitational pull that compress gas and trigger star formation. As these waves move through the galaxy, they act like traffic jams in space, slowing stars and gas and creating bright regions of activity. The spiral arms are home to vibrant stellar nurseries, where young, massive stars illuminate the surrounding gas clouds. The formation of the spiral arms was influenced by the Milky Way's interactions with smaller galaxies. These interactions disrupted the disk, creating ripples that evolved into the arms we see today. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius A star. Its mass, equivalent to 4 million suns, is concentrated into a region no larger than our solar system. Sagittarius A* is surrounded by a dense cluster of stars, many of which orbit at incredible speeds. These orbits provided the first evidence of the black hole's existence, as astronomers could calculate its mass based on the motion of nearby stars. While Sagittarius A* is relatively quiet now, it has likely experienced periods of intense activity. During these phases, it would have consumed vast amounts of gas and dust, emitting powerful jets of energy and influencing the distribution of material in the galactic center. Around 4.6 billion years ago, in a quiet region of the Milky Way's Orion arm, a dense cloud of gas and dust began to collapse under its own gravity. This event marked the birth of our solar system. At the center of this collapsing cloud, a young star ignited, the Sun. Around it, the remaining material flattened into a rotating disk, where particles collided and coalesced to form planetesimals. Over millions of years, these planetesimals grew into the planets, moons, and asteroids we see today. The Earth formed as a rocky planet, enriched with elements forged in the cores of ancient stars. Positioned in the Sun's habitable zone, it retained liquid water, a key ingredient for life. The formation of the solar system was a direct result of the Milky Way's long history of star formation, supernovae, and chemical enrichment. Every element in our bodies, from the iron in our blood to the calcium in our bones, was forged in the heart of a star. The Milky Way is a vast and dynamic system, home to hundreds of billions of stars, vast clouds of gas and dust, and invisible dark matter. It spans over 100,000 light-years and contains regions of intense star formation as well as quiet zones filled with older stars. The galaxy's spiral arms are bustling hubs of activity, where gravity compresses gas into dense clouds that give birth to new stars. In contrast, the central bulge is a dense region of older stars, surrounding the supermassive black hole at the core. The Milky Way is also part of a larger cosmic structure, the Local Group, a collection of more than 50 galaxies bound together by gravity. Its closest companions include the Large and Small Magellanic Clouds, two dwarf galaxies that orbit the Milky Way. The Milky Way's journey is far from over. In about 4.5 billion years, it will collide with the Andromeda Galaxy. This epic event will be a slow-motion dance, taking hundreds of millions of years to unfold. During the collision, gas clouds will compress, igniting waves of star formation. The central black holes of both galaxies will eventually merge, forming an even larger supermassive black hole. The resulting galaxy, often called Milkomeda, will be a massive elliptical system. Though its structure will be vastly different from the Milky Way, it will carry the legacy of both galaxies, preserving the stars, planets, and elements that once formed in their spiral arms. Even after this merger, the Milky Way's story will continue, as its stars drift through an ever-expanding universe. The Big Bang was the moment when time, space, and energy burst into existence. Before this cosmic explosion, the universe existed in a state of unimaginable density and heat, a singularity beyond our comprehension. Then, in a fraction of a second, this singularity expanded. Not into space, space itself was expanding, creating the universe. During the first fractions of a second, forces that govern the universe today, gravity, electromagnetism, and nuclear forces, separated from a unified state. Quantum fluctuations in the energy field left tiny ripples in the density of matter, which would later grow into galaxies and the cosmic web. As the universe cooled, the quark-gluon soup condensed into protons and neutrons, the building blocks of atomic nuclei. Within minutes, nuclear fusion created the first elements, hydrogen, helium, and trace amounts of lithium. The universe was now a sea of hot plasma, its light trapped by a dense fog of particles. Hundreds of thousands of years passed as the universe expanded and cooled. Finally, electrons combined with nuclei to form neutral atoms, allowing light to escape and travel freely. This light, the cosmic microwave background, is a snapshot of the early universe, revealing the seeds of cosmic structures that would evolve into galaxies like the Milky Way. But even after recombination, the universe remained dark for millions of years. Stars and galaxies had yet to form, and the vast expanse was filled with cold hydrogen gas. This era, known as the Dark Ages, persisted until gravity began to shape the first stars. Gravity is a relentless force, and over time, it pulled the hydrogen and helium gas into dense clumps. Dark matter, an invisible yet dominant form of matter, acted as the scaffolding for these structures, guiding the formation of the first stars and galaxies. In regions of high density, the gas became so compressed that nuclear fusion ignited, creating the first stars. These population 3 stars were giants, hundreds of times the mass of our Sun. They burned at incredible temperatures, producing intense light and heat. But they lived short lives, mere millions of years, and ended in spectacular supernovae. These explosions dispersed heavier elements, such as carbon, oxygen, and iron, into the surrounding gas, enriching it. These elements became the building blocks for the next generation of stars and, eventually, planets. The first galaxies began as small, irregular clusters of stars and gas. Over millions of years, they collided and merged, growing larger and more complex. The Milky Way's origins lie in this era, as one of countless proto-galaxies forming across the cosmos. The Milky Way's history is one of relentless growth and evolution. Over billions of years, it expanded by consuming smaller galaxies, a process known as galactic cannibalism. These mergers shaped the structure and composition of the galaxy, leaving behind telltale signs visible to astronomers today. Stellar streams, long arcs of stars stretched across the sky, are remnants of smaller galaxies torn apart by the Milky Way's gravity. These streams provide a glimpse into the galaxy's tumultuous past, offering clues about its growth through mergers. One of the most significant mergers occurred around 10 billion years ago with the Gaia-Enceladus galaxy. This event added a substantial number of stars to the Milky Way, forming its thick disk and enriching it with heavier elements. The collision also triggered waves of star formation, lighting up the galaxy. The process of galactic cannibalism continues to this day. The Sagittarius dwarf galaxy, for instance, is currently being pulled apart, its stars gradually joining the Milky Way. These ongoing interactions highlight the dynamic and ever-changing nature of our galaxy. The Milky Way's transformation into a spiral galaxy began as it grew larger and more organized. Around 9 billion years ago, it settled into a rotating disk, influenced by angular momentum and gravitational interactions. The spiral arms are a product of density waves, regions where stars and gas are more concentrated. These waves move through the galaxy, compressing gas clouds and triggering the formation of new stars. The process is self-sustaining, with each generation of stars creating the conditions for the next. The spiral arms are not static. They are shaped by the galaxy's rotation, interactions with satellite galaxies, and the motion of stars and gas. Over billions of years, they have evolved into the iconic structure we see today. Within the arms, massive clouds of gas serve as stellar nurseries. These regions are dynamic and chaotic, with gravity pulling material together to form dense clusters of stars. The bright, young stars that emerge illuminate the arms, creating the stunning patterns visible in images of the Milky Way. At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole that exerts a profound influence on the galaxy. With a mass of about 4 million suns, it is an invisible powerhouse, its gravity shaping the orbits of nearby stars. Sagittarius A** is surrounded by a dense cluster of stars, some of which travel at incredible speeds. By observing these orbits, astronomers have been able to measure the black hole's mass and confirm its presence. While it is relatively quiet now, Sagittarius A** likely experienced periods of intense activity in the past. During these active phases, it would have consumed vast amounts of gas and dust, emitting powerful jets of radiation. This activity may have influenced the distribution of material in the galaxy's central regions, shaping its evolution. The existence of supermassive black holes is a common feature of large galaxies. Their formation and role in galaxy evolution remain active areas of research, offering insights into the dynamics of the cosmos. About 4.6 billion years ago, in a quiet corner of the Milky Way's Orion arm, a dense cloud of gas and dust began to collapse under gravity. This marked the beginning of our solar system. At the center of this collapsing cloud, a young star ignited, the sun surrounding it, the remaining material flattened into a rotating disk, where particles collided and stuck together. Over millions of years, these particles grew into planetesimals, the building blocks of planets. The Earth formed in the inner region of the disk, where temperatures were high enough to vaporize lighter elements. This region gave rise to rocky planets, while the colder outer regions produced gas giants like Jupiter and Saturn. The solar system's formation was a direct result of the Milky Way's long history of star formation and chemical enrichment. The elements that make up our planet, and even our bodies, were forged in the hearts of stars and scattered across the galaxy by supernovae. The Milky Way is a dynamic system, constantly changing and evolving. Its spiral arms are regions of intense activity, where new stars are born from clouds of gas and dust. The galaxy contains hundreds of billions of stars, along with vast quantities of gas, dust, and dark matter. The central bulge, a dense region of older stars, surrounds Sagittarius A star. Meanwhile, the halo, an extended region of the galaxy, is home to ancient globular clusters and the remnants of past mergers. The Milky Way is also part of the Local Group, a collection of more than 50 galaxies bound together by gravity. Its closest companions, the Large and Small Magellanic Clouds, are dwarf galaxies that orbit the Milky Way, contributing gas and stars. The Milky Way's story will continue for billions of years. In about 4.5 billion years, it will collide with the Andromeda Galaxy, initiating a slow and spectacular merger. During the collision, gas clouds will compress, triggering waves of star formation. The central black holes of both galaxies will merge, forming an even larger supermassive black hole. The resulting galaxy, often called Milkomeda, will be an elliptical system, marking the next stage in the Milky Way's evolution. Despite these changes, the legacy of the Milky Way will endure, carried by its stars and the elements that once formed planets and life. Even after the merger, the Milky Way's remnants will drift through an ever-expanding universe, part of the endless cycle of cosmic creation and transformation. Before the birth of the Milky Way, there was only the universe, a vast, empty canvas waiting to be filled. The Big Bang, occurring approximately 13.8 billion years ago, marked the beginning of everything. From a point smaller than an atom, the universe expanded exponentially, unleashing a torrent of energy that would eventually